Welcome to part 2 of our lesson on first-order ordinary differential equations. Today we focus on applying numerical solvers to physical models, handling coupled equations, and learning how to interpret and validate our results computationally. By the end of this session, you should be able to formulate first-order models for physical systems, such as RC circuits and falling bodies. You will also learn how to solve coupled systems and perform essential checks to ensure your numerical solutions make physical sense. Let us begin with a quick recap. A first-order ODE relates the rate of change of a variable to the variable itself and time. To solve it with SciPy's ODEnt function, we need a derivative function, an initial condition, and a time array. We start by importing our standard tools: NumPy, Matplotlib, and ODEnt. The output confirms our packages have loaded successfully. We are now ready to tackle our first physical model. Our first example is an RC circuit, where a capacitor charges through a resistor. The differential equation models the approach to equilibrium, driven by the difference between the battery voltage and the capacitor voltage, scaled by the time constant. We set up this model in Python by defining our physical parameters and the derivative function. Then, we use ODEnt to solve for the voltage over a time span of 6 time constants, and we prepare to compare it against the known analytical solution. Here is the resulting plot. The solid line is our numerical solution, and it perfectly overlaps the dashed analytical curve. Notice how the voltage rises quickly at first, then gently levels off at the 5-volt equilibrium limit. The console output verifies our time constant of 2.0 seconds. It also shows the voltage after one time constant, which gives us a quick numerical check on the charging progress. To interpret this, recall that after one time constant, the capacitor reaches about 63% of its final voltage. This simple exponential relaxation is a mathematical pattern you will see frequently in cooling, population dynamics, and pressure models. Next, let us look at an object falling under gravity with linear air resistance. The rate of change of velocity depends on gravitational acceleration minus a drag term. Eventually, the acceleration reaches zero, defining a terminal velocity. We define our mass, drag coefficient, and gravity, then write the derivative function for velocity. We call ODEnt to solve this over a 20-second interval. And we also compute the acceleration by plugging our velocity solution back into the derivative function. With the numerical solution complete, this code prepares our visual diagnostics. We set up 2 plots: one to track how the velocity changes over time, and a second to monitor the acceleration curve. This final block of code displays our plots and prints a comparison between the theoretical terminal velocity and our computed final velocity. Looking at the first plot, the velocity starts at 0, climbs steeply, and then smoothly asymptotes to the theoretical terminal velocity, shown by the dashed line. The second plot confirms the complementary behavior. Acceleration begins at 9.81 meters per second squared and decays towards 0 as the object stops speeding up. Our printed output shows that the computed final velocity is extremely close to the expected terminal velocity. This gives us confidence in the accuracy of our numerical integration. These physical reasonableness checks are critical. A plot might look smooth but still be entirely incorrect if the parameters, units, or equations have an error. Always verify your starting and ending behaviors. Now let us move to coupled first-order ODEs. Suppose we have 2 compartments exchanging some quantity. The rate of change for one depends on the other. For ODEnt, we pass our initial state as a list containing values for both variables. We define an exchange rate function that unpacks the current state, computes the derivatives, and returns them as a list. We then call ODEnt and prepare to plot the individual quantities alongside their sum. This code displays the plot and calculates the maximum deviation in the total quantity. Since the model only transfers material between compartments, the sum should ideally remain constant. The output shows our solution array has 2 columns, one for each variable. It confirms our initial conditions and shows how the quantities balance out to 50 units each by the end of the simulation. The plot visualizes this exchange nicely. One compartment loses quantity, while the other gains it until they reach equilibrium. Importantly, the dashed green line representing the total remains perfectly flat over time. The printed output confirms that the maximum change in the total quantity is essentially zero, restricted only by the floating point precision of the machine. When working with coupled systems, remember that the output array contains one column per dependent variable. Passing the initial conditions as a list is what allows ODENT to handle multiple equations simultaneously. As we have seen, a solver is not a black box. We must validate our results by checking initial conditions, limiting values, and conservation laws. To illustrate the impact of numerical settings, we will now implement a manual Euler solver. We define a basic Euler stepper and calculate a high-resolution reference solution using ODENT. Then, we iterate through several different time steps, applying our manual Euler method to the terminal velocity problem. This code finalizes the formatting and displays the plot, which will help us visualize how the choice of time step directly impacts the accuracy of a simple numerical method. Look at how the different time steps behave. With a large 2-second step, the Euler method overshoots and behaves poorly. As we decrease the step size, the numerical approximation converges closely to the exact reference solution. This diagnostic clearly demonstrates that time step size matters. While ODENT uses advanced adaptive algorithms to manage this automatically, you are still responsible for ensuring the output makes physical sense. Before we finish, let us review some common pitfalls. First, remember that your function must return the derivative, not the solution. Second, a differential equation requires a clear initial condition to be solvable. Third, pay attention to the argument order in your derivative function. Fourth, for coupled systems, ensure you return exactly as many derivatives as variables. Finally, understand that your output is an array where columns represent your variables over time. Mistake 6 is using inconsistent units, which will ruin the timescale of your model. Mistake 7 is blindly trusting a smooth graph without doing the basic physical checks we discussed today. Let us put this into practice. For your guided exercises, try tweaking the capacitance in the RC circuit to see how the time constant reacts, or adjust the drag coefficient in the falling body model. You can also experiment with different initial states in the coupled system, or deliberately break the derivative function to see how the solver complains. Here is a starter cell for modifying the RC circuit. This portion of the starter code runs ODENT with the new parameters, creates a plot of the capacitor voltage, and prints the updated time constant and final voltage. With our modified parameters, the capacitor now takes longer to charge, asymptoting smoothly to the new 9-volt battery limit. The output confirms our new time constant is 3.0 seconds, and the final computed voltage accurately approaches the expected 9 volts. To summarize, modeling first-order ODEs requires translating physical laws into code, applying a solver, and critically evaluating the results. Mastering this process is essential for tackling more complex, multivariable dynamical systems in computational physics.